Alright, so for this lesson, we'd like to solve equations that have square roots or cube roots and so on within them. So for example 1, I'll show you a really basic strategy that will work for more complicated equations. So let's start with the square root of x minus 1 is 3. You probably can even guess what the answer to this problem is, but I want to go through it a little bit more carefully. So like what number that when I put it in place of x makes the left side equal the right? A good strategy is to get the root part all by itself. So to do that, I'm going to add 1 to both sides. Now, again, you could just like look at this and probably know, oh, right, the solution is going to be 16 because the square root of 16 is 4. But if you remember that the square root has an exponent of 1/2, and squaring is the opposite of square rooting, a common strategy is to just square both sides of your equation, because squaring a square root cancels it to x, and squaring 4 gives you 16, which is the answer that I expected. So this is our strategy. Get the root part by itself, and then in this case, square both sides. So how is this different if we compare it to, let's say, the cube root of x minus 7 is equal to -1? Here, the root part is completely by itself, the cube root, and the goal will be to get rid of that symbol. If you have a square root and you square both sides, if you have a cube root, you will cube both sides. And the reason is, the cube root and cubing will cancel each other, and what is left over is everything that is underneath the root symbol, which is just x minus 7. So this example looks a little bit different than the one we just did because there was more stuff under the root symbol, but I still got the whole thing by itself, and then I raised both sides to the power of 3. Okay, if I cube -1, the other side, -1 times -1 times -1, it still is -1, and to solve for x, I would just add 7 to both sides. And so I get 6. And you can check in the original equation that it makes it a true statement, and it does. 6 in place of x would give you -1, and the cube root of -1 is actually -1. So a very simple strategy, but it'll work on more complicated equations. Maybe just one final thought. What if, I'll go back to that very first equation, and I'm going to switch it up slightly. So the square root of x minus 1, what if it was equal to -3 instead of +3? If we use the same strategy to find the solutions, I would start by adding 1 to both sides. And actually, at this point, I know there could not be an answer to this equation. If you take the square root of a number, it's always positive. There's no way it could ever equal a negative number. I know there's no solution to this equation. But if you use our strategy of squaring both sides, you still get x on the left, and you get 4 on the right. And this is where you have to be careful. It's a really simple strategy for solving root equations, but it potentially might give you something that's not a solution. And our way around this is, whenever we get an answer, we'll plug it back into the original equation and see if it works or if it doesn't. So the good news is that this strategy will give you all of the solutions, but sometimes it'll throw in an extra one too that does not work in the original equation. So basically what we do is we note that it's not a solution, we throw it away, and we are done with this example. Okay, so for example 2, again, the strategy here is to get the square root portion by itself. Very easy to do because I can just subtract 2 from both sides. So this equation is the square root of x plus 10 is equal to x minus 2. And the only thing we can really do at this point is either like try to guess the answer or use our strategy of square both sides. And it's great on the left because you just get x plus 10. But on the right you have to be careful because this is x minus 2 times x minus 2. We get, when you distribute 4 terms, so I have to be careful to write all of those out. We have x squared minus 2x, then we have minus 2x plus 4. So to be careful here, whenever you square something that's separated by a plus or a minus sign, you might have several more terms than you would initially think. The rest is now just to take my equation, combine some like terms. Let's see, we get x squared minus 4x plus 4. Okay. And to solve this equation, we've done these before. This is a quadratic. I think what I'll do is set one side equal to 0 by subtracting x and subtracting 10. Maybe this thing will factor and I can guess my answers from that. So if I subtract x and 10 from both sides, I get x squared, I get minus 5x, and I get minus 6. And I'm hoping that this factors nicely into two pieces. Let's see. And it does. I get negative 6 and a positive 1. That multiplies to negative 6, adds to a negative 5. And from here, I can see that 6 appears to be a solution. And then from here, that negative 1 appears to be a solution as well. So there we go, right? Two solutions to my original equation of x plus 10 plus 2 is equal to x. But we gotta be careful. I mean, maybe neither of these are solutions, or maybe they both are solutions. Our way is to just kind of plug it in and check to see what happens. So let's see. I'll try 6. I get 6 plus 10, then I have plus 2 is equal to 6. That's the square root of 16 plus 2 is equal to 6. Ah, right, 4 plus 2 is 6. Great, this is good. But what about negative 1? If I take negative 1 and I plug it into this equation, I get negative 1 plus 10 plus 2 is negative 1. This isn't looking good. I have a negative number on the other side. This is the square root of 9 plus 2 is negative 1. 3 plus 2 is negative 1. No, that's not true. 5 isn't negative 1. That's false. So what that means is this is an extraneous solution. It's actually not something that makes the original equation true. So through all this work, 6 works, but negative 1, the only other possible choice, didn't work in our original expression, and this is the answer to this example. All right, so for the final example, the square root of x plus 8 plus the square root of x plus 3 is equal to 5. This is actually kind of a tricky one, so I'll try to present it as best I can, but the goal here is to isolate one of the square roots. I'm not going to square both sides because I think that's going to create this like giant mess. So I'm still going to use the same strategy. I'm going to rewrite this equation as, I'll go with the square root of x plus 8 is equal to 5 minus the square root of x plus 3. So I'm still like getting one of those square roots alone, but unfortunately I got this other one on the other side. So let's see if this helps. I square the left, and I have to be careful when I square the right. The left, it's great. I just get x plus 8. But on the right, just being a little bit careful here, 5 minus the square root of x plus 3 squared means I'm going to have several terms to be careful with. Like 5 times 5 is 25. Then I multiply the 5, I get 5 times the square root of x plus 3. Then I get another minus 5 times the square root of x plus 3. And then I get plus, actually I just get x plus 3. So what I did there was, I took the 5 and I multiplied it to both terms, which gave me 25 and minus 5 times the square root of x plus 3. And then multiplied this in, which was, again, negative 5 the square root of x plus 3. But then this term times this term became positive, and the square root times the square root just canceled to the x plus 3. I'm going to simplify all of this. Let's see. I have 25, and that 3 at the very end is 28. I have a plus x that can't be combined with anything, but I also have minus 10, the square root of x plus 3. So that's what I mean by being careful. Like the right side, there was no way around it. It was kind of messy, but when I square it, this is what I end up with. Okay, I think now what I'm going to do is subtract x and 28 from both sides, and I get negative 20 is equal to negative 10 times the square root of x plus 3. Oh, okay, I'm going to divide both sides by negative 10. That gives me 2 is equal to the square root of x plus 3. This actually goes back to an equation like what we had in our first example. It's just one square root equaling one number. I can now just square both sides. And what happens is I get 4 is equal to x plus 3. I subtract 3 from both sides and I get 1. And that appears to be the solution. I'd have to check this, like nothing else could work. I'll go back to my original equation and I get 1 plus 8 plus the square root of 1 plus 3. Is that equal to 5? The square root of 9 plus the square root of 4. Is that 5? 3 plus 2 is. Yeah. And nothing else could possibly work, so I in fact know that 1 is the solution, in fact the only solution to this equation. So just a couple of takeaways. The original question had 2 square roots, so it was no surprise that this concept of squaring both sides had to happen twice. The first time was really messy because of this right side. It came out with a bunch of terms, some of which could be combined. But then, a little bit of work simplified it down to something that just had 1 square root, and I was able to square both sides to get my final answer of just x is equal to 1. So that is it for this example.